Hello. Okay. Okay. Let me share the screen. Okay. So I suppose we finished our discussion with multilayer perceptron in the previous lecture. So in the end, we talked about an example. We discussed an example uh, in the last lecture. So this was the example that we had discussed. Just a minute. Yes. So this was the example that we had discussed in the previous lecture, where we were trying to identify what is the output of this multilayer perceptron that we had created. And using the backpropagation algorithm, we tried to update the values of weights by calculating the error in the hidden layer from the hidden layer to the output layer, as well as by calculating the error from input layer to the hidden layer, right? I suppose everyone is clear with the example and how to perform the calculation. Yes or no? Everyone is clear with the example, right? Okay. So here we have ended our discussion with the backpropagation algorithm. Two, 3 points that I want to wish to discuss regarding the multilayer perceptron is one is regarding the learning rate. Before that, we'll talk about activation function. So I'm stating one statement that saturated activation function. So whenever we are utilizing sigmoid activation function, it is going to get saturated after a point of time. If you see, so in multi-layer perceptron, what is the case is we'll be having multiple hidden layers. There is a possibility at this point of time in the example that you are seeing, there is only one hidden layer that is present in this multi-layer perceptron. But there is possibility that there will be multiple hidden layers present in your multi-layer perceptron. More deep network will be created, fully connected deep network, and in that case sometimes the sigmoid activation function will actually saturate after a point of time. Can you identify what kind of problem will a sigmoid activation function will face after a point of time? Can you identify that? Yes, yes. So in the derivative of a sigmoid activation function, it was something like 1 minus sigmoid into 1 minus sigmoid. Okay, this kind of derivative is there for the sigmoid activation function, right? So if the value of sigmoid is suppose close to 1, there is a possibility derivative of this, the derivative value will be close to 0. Yes, it will be close to 0. Then ultimately, okay, the voice is breaking in between. Just a minute. Wait for 2 minutes. Okay, wait for 2 minutes. Okay. Let me know if the voice is breaking, still breaking. Is the voice okay now, or is it still okay? Okay, it is not breaking, right? Okay, so our discussion was, so in the case of sigmoid activation function that we have, so the weight after, so we saw that the derivative of a sigmoid activation function is something like this. Okay, derivative of sigmoid activation function is sigmoid into 1 minus sigmoid. And if the value of sigmoid reaches close to 1, that is 0.99 or something, the derivative value will be close to 0. So ultimately, the weight update that is happening um, after a point of time in the hidden layers and following till the output layer, it is possible that the weight update will be very small or maybe insignificant after a point of time. So this is one problem that we might face in the case of using a sigmoid activation function, which saturates after a point of time. That's why we may be utilizing different activation functions. So we have ReLU activation function, TANH activation function. These are an alternatives that we have for a sigmoid activation function. So right now, I'll not be going in depth of what a ReLU activation function is and TANH activation function is, but I suppose that the main idea of utilizing different activation function is to avoid the saturation of that is happening in the case of sigmoid activation function. Is this clear? Is this point clear in the case of backpropagation algorithm? Okay. Okay, another point that I wish to share here is there is a possibility of using different learning rates in different layers. Okay, if you see certain research papers also, they might be using, there are possibilities of using adaptive learning rate. Okay, there is a point called adaptive learning rate where we may be initially using certain random learning rate, for example 0.01 as a learning rate, and we may keep on increasing the learning rate as we reach the final layer. Okay, something like this is also there, but mostly this point, different learning rates in different layers. Why do we use this? One point is because of the saturation in the derivation, saturation in the case of weight update rule. That's why we may use different learning rates in different layers. For example, in the initial layers where the saturation will be less, we might use a lower learning rate, and in the proceeding learning rate, that is after the forward propagation, whenever we are reaching close to the output layer, we might use larger learning rate because the sigmoid activation function will be saturated by that point of time. And in order to maintain that, in order to balance that, we might use a larger learning rate. Are you getting the point here? Why do we require there is a possibility of using different learning rates in different layers? Are you getting the point? Why do we use it? Yes or no? Yes. Okay. So is it clear to everyone why we might use different? Okay, larger lead, that's what I was talking about. See, in the case of output layer, whenever we are reaching more number of layers are there is a possibility that the sigmoid value that we discussed, the derivative of the sigmoid that we are discussing, will be saturated. That is, it will be close to 0. So in order to balance that, we'll be using larger learning rate whenever we are reaching close to output layer or in the following layer. Are you getting the point now? Yes or no? Yes. Okay. So I suppose these 2 points are clear in the case of backpropagation algorithm. And so here our backpropagation algorithm is over, and we have completed our discussion with the multilayer perceptron. So in the multilayer perceptron, we started our discussion by why did we start with the multilayer perceptron? What is the reason of using multilayer perceptron? Where we also discussed the XOR problem. That is what was the inspiration behind utilizing, behind creating the multilayer perceptron. And later on, similar to what we were doing in the case of linear regression and logistic regression, where we were trying to update the weight and to minimize the loss, in the similar manner in the MLP theory, where multilayer perceptron is there, we are trying to, first of all, we are initializing the weights randomly. Then using backpropagation algorithm, where we are propagating the error backwards, we are trying to update the weights associated with all the connections that are there in your multilayer perceptron in order to achieve the minimum loss, right? So we also went through the derivation part, where we tried to identify the two different derivative for error values for the hidden layer as well as the output layer. So I suppose everyone is clear with the theory of backpropagation as well as multilayer perceptron, right? So now we'll be proceeding with another topic in the last the another topic with the classification algorithm, that is support vector machine. So we'll be today starting our discussion with support vector machine. So everyone is clear up to this? Shall we start our discussion? Any doubt in any calculation or anything? Okay. Also, I would like to point this out that in the case of the multilayer perceptron diagram that we have here, there is a possibility of adding a bias term here as well. Okay, so you have to identify that there is a possibility that you will be adding a bias term here as well as a bias term here, as well as some bias term over here as well, right? So so if you try to solve, I'll add one more example for your understanding. Whenever I upload, I'll update the PPT and I'll add one more example for your better understanding. Are you getting the idea? What I'm trying to say here? Yes. All right. So let us start our discussion with support vector machine now. Okay, so today we are going to start with another classification algorithm. Right now we'll be discussing the theory in respect to classification for support vector machine. Later on we'll also discuss how it will go through regression and all. But right now our discussion will be suffice to classification using machine support vector machine. And what are the conditions that are first we'll talk about linear in the case of linear SVM, and later on we'll discuss about non-linear SVM. Okay, so this support vector machine is actually from the class of logistic regression only. In the case of logistic regression, if you recall, the classification was performed based on a condition that we had, that the data should be linearly separable. Okay, data should be linearly separable. And right now we'll be talking about binary classification in case of support vector machine, where the data is required to be linearly separable. Okay, so what were we trying to do in the case of logistic regression? If you recall, in the case of logistic regression, we had suppose there is a two-dimensional data set we have. Suppose these are the data that we are having, XXX, and these are the negative samples. And suppose we have some positive samples over here. This red dot represents the positive samples and black represents the negative samples. So what we are trying to find is, we are trying to find an hyperplane such that it divides, it tries to classify, it tries to linearly classify such that your data is linearly separable. The data needs to be linearly separable, and we are finding an hyperplane that divides our data, so that divides our data properly, so that whenever a new sample is there, you can easily classify in which class does it belong. Does it belong in W1, or does it, sorry, let us say C1, or does it belong in class 2, C2? Okay, that is what we were doing in the case of logistic regression. But there is a certain update in this particular problem that we are doing using the support vector machine. Okay, so if you recall, in the case of logistic regression, we had a value. We were calculating this the distance. We were calculating the distance using Wx plus b. Yes or no? We were calculating the distance, and if the distance is greater than 0, it was in the positive side of the hyperplane, and if the distance was less than 0, it was on the negative side of the hyperplane. Are you recalling this part from the logistic regression? Yes or no? Just let me know. Yes? Okay. So now what we are trying to do in the case of support vector machine is so in this case, there may be multiple hyperplanes that may be dividing your data. Okay. So for example, this is one hyperplane. Let us say P1. I'm denoting this hyperplane as P1, is one of the hyperplane that is separating your linearly separable data. Okay, there may be another hyperplane, suppose P2. Okay, P2 is one of the hyperplane which is trying to separate your data, and there is another hyperplane P3 which is also separating your data properly. But how to identify which hyperplane is optimal? Okay, which hyperplane out of all these hyperplanes are optimal to which for dividing your data? So in that case, support vector machine comes into picture, where support vector machine tries to identify that hyperplane such that the distance, the margin distance is highest. Whichever hyperplane has a margin distance highest, that will be considered as your optimal hyperplane. Now, the question might come that what is margin and what are this? How do we identify this margin? So let us see that one first. So, for example, in your data set that you have, this is the hyperplane. For example, this is the hyperplane that is separating your linearly separable data. These are your data sets that you have. These are negative samples. These are positive samples. Okay. And margin will be the distance. For example, margin will be the distance of this. For example, this is a positive hyperplane. Okay. We'll be drawing a positive hyperplane in the positive side, of our data, and we'll be adding a hyperplane in the case of negative side as well, where it will be passing through a data point which will be closest, which is the closest data point to the hyperplane, which is known as support vector. So this is known as support vector. This is known as support vector. Similarly, this point, which is the closest point in the to the hyperplane that we are drawing, this is also support vector. Are you getting what is the support vector? So the nearest data point on each side of the hyperplane, nearest data points on each side of the hyperplane are known as the support vectors. There will be, okay, in the positive side of the hyperplane, there will be positive samples. In the negative side of the hyperplane, there will be negative samples. So the nearest data points on each side of the hyperplane are known as the support vectors. So if you see, if your data set is something like this, and there is a hyperplane which will be passing through the nearest data point. Okay, wait a minute. So that is a hyperplane, and these are the data points that you have. Suppose these are the negative samples, these are the positive samples, and the hyperplane which are passing through the nearest data point, the points, okay, that are nearest to the hyperplane, points that are nearest to the hyperplane on either side. Okay, these are known as support vectors. So in this case, these two will be the support vectors which are nearest to the hyperplane that is separating your data. Okay, in this case, these will be the support vectors. So these are the support vectors in the case of negative side of the hyperplane, and these are the support vectors in the case of positive side of the hyperplane. Are you getting the point? What are known as support vectors? Yes or no? Yes. Okay. Yes, you can work for multi-class as well, but right now we'll be talking about binary classification only. Okay, right now our discussion exclusively is for binary classification. Later on we'll come to multi-class classification. Okay. No, SVM is not used by logistic regression. SVM is a separate classification algorithm, which is a update to the logistic regression algorithm that we have studied. So in the case of logistic regression that we had studied, we were just creating a hyperplane to separate our data. But in this case, we are adding an additional additional idea that we are trying to maximize the margin distance. That is, what is the margin distance in this case? It is an update to the logistic regression algorithm that we have. Okay, are you getting the point there? It is not used by logistic regression. Okay, so what we are trying to do is we are trying to maximize the margin distance that we have. So what is the margin distance? This is the distance of this is the margin that we have. We are trying to maximize this. Whichever hyperplane that you are creating, whichever hyperplane that you are identifying to separate your data, to classify your data, if that hyperplane has maximum margin distance, then that hyperplane will be considered for separating your data. For example, we may have another hyperplane like this, which is separating our data, and we may identify the margin distance to be something like this. Okay, let us say this is the margin distance that we have. And if the margin distance of this hyperplane is greater than the margin distance of the hyperplane P1, P2. If the margin distance of P1 is greater than P2 is greater than margin distance of P1, then P2 will be considered as an hyperplane to separate your linearly separable data. Are you getting the point here? What is the margin distance? Yes or no? Yes, margin distance is the distance between two support vectors. Yes, and the support vectors on the support vectors between on the positive side of the hyperplane and on the negative side of the hyperplane. That is the margin distance that we have. Okay, so for each side. So, for example, if we have if we are having a data set like this. So suppose this is the hyperplane that we are creating. This is the hyperplane. We'll be identifying the equation of an hyperplane that separates our data such that the margin distance is maximum. So we'll be creating a hyperplane on the positive side of the data as well, and we'll be creating a hyperplane on the negative side of the data as well. And we'll be trying to maximize this distance. The maximize. Suppose I am indicating this distance as d, then I'll be trying to identify an equation of hyperplane such that this distance is maximized. Are you getting the point now? What we are trying to do in the case of support vector machine? Yes or no? Yes, in the binary classification we'll be having, so what is the idea is support vectors are the data points that are nearest to the hyperplane. Okay, the most nearest to the hyperplane. So in this case, in the positive hyperplane, we are having two support vectors on the positive side of the data, right? In this case, in the negative hyperplane, we are having support vectors. For example, this is a point that is nearest to the hyperplane that we have identified to separate our data. So in this case, these are the support vectors. So there can be multiple support vectors on each side. So mostly in the case of binary classification, there will be support vectors for the positive class of data, and there will be the support vectors for the negative class of the data. Are you getting the point now? Yes or no? No, support vectors is not equals to number of classes. Support vectors are those points that are nearest data points on each side of the hyperplane. Okay, so in this case, nearest data points on each side of the hyperplane means, so this is the hyperplane that we are utilizing to separate our data. Okay, let us use different color. So for example, this is the hyperplane that I have identified. I will identify an equation of an hyperplane to separate this data. And these are the data points that we have on the positive side of the hyperplane. And these are the points, the data points that I have identified on the negative side of the hyperplane. So which is the point that is nearest to the hyperplane that I have identified? On the positive side, these are the 2 points that I have identified, okay, which are on the nearest to the hyperplane that I have created to separate this data. Similarly, this is the support vector that I have identified on the negative side of the hyperplane, which is nearest to the hyperplane. Okay, so it is not equal to number of classes. The idea, support vectors can be multiple, but the idea is for right now we'll be having two class classification. So there will be support vectors associated to positive data points, and there will be support vectors associated to negative data points. Are you getting the point now, or is it still confusing? Okay, all right. So now, we are trying to maximize the margin distance. So train data set to minimize distance from support vectors. No, actually maximize the distance. We are trying to maximize the distance from support vectors. Yes or no? Right now, what are we trying to identify is we are trying to maximize this margin, whichever hyperplane equation that will be identifying. In the case of for error, by error, do you mean that some of the points on the negative side and some of the points on positive side? Do you mean that? Yes. Then, can you elaborate what you are trying to? Okay, in error from point to, okay. To reduce the error, right. So our point is we want to maximize the confidence. Okay, so for example, if the point is at a maximum distance from this point, from this line, suppose a new point that we have identified is at a maximum distance. Suppose this is a new point that we are trying to classify this particular point in based on the hyperplane that we have created. So if the distance is maximum from this hyperplane, then the confidence of this in the confidence of this particular data point in positive class will be higher. Yes or no? In comparison to this particular point which is nearer to the hyperplane. That is why what our main idea is to maximize the margin distance so that the confidence of classifying the new data points in appropriate class is highest. Are you getting the point now? Yes or no? Okay. Okay. So that is the main idea in this case of support vector machine. So this is an update to what we studied in the case of logistic regression, where we were just identifying the hyperplane to separate our data. Okay, so we were just identifying the hyperplane, and based on that, we were also identifying the probability of a new data point on a particular site. For example, our output was based on the distance. First, we were calculating the W transpose X, the distance of that particular point from the hyperplane that we have created, and based on if the value is based on that value, we were trying to identify what is the probability of that particular point in the positive class and what is the probability of that particular point in the negative class. Okay, that was our idea. So we were just identifying a hyperplane, but in this case, we'll be trying to identify a hyperplane such that our distance, our margin distance is maximum. That is the main idea. Margin distance is maximum. So this is the point that we have updated in the case of support vector machine. Okay, I suppose the main idea behind support vector machine is clear to everyone. Yes or no? Yes, there is no necessity that support vectors is two. There can be more than two support vectors at a point of time. So as I showed to you in the example here also, so that in the positive side there are two support vectors, because my data points are such that I have mentioned only two support vectors on the positive side. Support vectors are those points which are closest to the decision boundary, closest to the hyperplane that I have created, the nearest points to the hyperplane on the positive side. So there can be more than two support vectors also. Suppose I am creating one more support vector over here, which is nearest to the hyperplane that I have created. Okay, there can be more than two support vectors on each side. Are you getting the point? There is no relation between binary classification and the number of support vectors. Just try to understand that you are not, there is no relation between these two. The idea is what is support vectors that you have to understand at this point of time. What is support vector? Support vector is the example that is closest, the data point that is closest to the hyperplane on each side. Okay, that is nearest to the hyperplane on each side, and we are trying to find a hyperplane which maximizes the distance between these support vectors. Okay, on the positive side and negative side, we are trying to find a hyperplane that maximizes this distance. Okay, I hope everyone got the point. Yes or no? Okay. Okay, just a minute. All right. Okay, so now that we have defined the primary idea behind support vector machine, the primary idea is set, why we are utilizing support vector machine and what is the main idea behind support vector machine. That is to find a margin, find a hyperplane equation such that the margin distance is highest. Okay, margin distance is highest. Now, as we had studied in the case of linear classifiers, if you recall, what were we trying to do? We were trying, in the case of linear classifiers that we have studied, we were trying to identify the values of, for example, in the case of linear regression, we were trying to identify the values of W1, W2, and W3 and values of parameters such that the loss is minimum. In the case of logistic regression also, we were trying to identify the values of the parameters such that the loss is minimum. We were utilizing binary cross entropy loss in the case of logistic regression. In this case also, we were trying to identify the margin, equation of a margin, will identify an equation of a margin, and we'll try to maximize the margin value, and we'll also optimize this particular algorithm. So in the case of logistic regression and linear regression, we were using different optimizer. What was the optimizer that we were utilizing in the case of linear regression and logistic? Which was gradient descent optimizer that we were utilizing. Gradient descent optimizer. In this case, we'll be using a different optimization algorithm. Primarily, we'll be utilizing an optimization algorithm that is Lagrange multipliers. We'll be utilizing Lagrange multiplier to perform the optimization process. And why we'll be utilizing this will also come to that point. So first, let us start with defining the equation of the hyperplane. First, let us start with defining the equation of the hyperplane that we have. So for example, we'll be making certain assumptions. We'll be making certain assumptions in the case of support vector machine, such as first assumption that we'll be making is what is the equation of hyperplane that we have. Equation of hyperplane. So if you know, hyperplane is actually in the 2D, 3D dimensional data. Normal line equation will be y is equal to mx plus c, right? So in the case of hyperplane equations that we'll be creating, which is of n dimensions. So for example, right now we'll be talking about only 2-dimensional data. So it will be something like W transpose X plus B is equals to 0, something like this. This is the hyperplane equation that we'll be utilizing. This is an assumption that we are making. Okay. Are you getting the point? This is an assumption. So in normally the hyperplane equation will be something like this. For n-dimensional data, it will be W1 x1 plus W2 x2 plus Wn xn plus W0 is equals to 0. Something like this will be in the n-dimensional hyperplane. Okay. If you know, in the case of 2-dimensional, there will be this hyperplane will be a line. In the case of 3-dimensional, this hyperplane will be a plane. In the case of 4-dimensional and so on, this is something the hyperplane equation will be of the form. But right now we'll be utilizing a normal in a vector form. We'll be considering this in a vector form, and this is the hyperplane equation that we'll be utilizing. And we'll be trying to find the equation of a hyperplane. We'll be trying to find the equation of a hyperplane such that it divides our data so that our margin distance is highest. Okay, so first we are defining what is the hyperplane equation. This is the equation of an hyperplane. This is an assumption that we are making. So suppose this is the equation of the hyperplane that we are utilizing to separate our data. Okay, this first assumption is clear to everyone, right? Yes or no? Okay. Now on either side, so now we have a support vector. We have certain data points on the negative side of the hyperplane and certain data points on the positive side of the hyperplane, and we'll be having certain support vectors. So the in the case of this, for example, this is a support vector, which is the point that is nearest to the hyperplane that we have created. Similarly, in this case, for example, these are the support vectors. So these are the points that are nearest to the hyperplane that we have created. So for each of this, we'll be creating an hyperplane. Okay, we'll be creating a hyperplane that passes through the support vectors in the positive side as well as negative side. Yes or no? We'll be creating hyperplanes and we'll be defining the equation because we want to find the distance. We want to find the margin distance. So we need hyperplanes on both sides, so that we can identify what is the margin distance and which equation do we need to maximize in order to identify the optimal hyperplane. Are you getting the point? So we'll be defining the equations for positive. Okay. Yes. So what we'll be doing is we'll be defining the equation. We'll be defining the equation of the hyperplane of the positive side, and we'll be defining the equation of the hyperplane on negative side. And for our mathematical convenience, for example, this hyperplane on positive side will be something like it. W transpose X plus B is equals to 1 and W transpose X plus B is equals to -1. These are the set of equations of hyperplane that we have created, this family of hyperplane equations that we have created, where the hyperplane equation is W transpose X plus B is equals to 0. This is the hyperplane equation, and the hyperplane equation on positive side is W transpose X plus B is equals to 1, and W transpose X plus B is equals to -1 on negative side. Are you getting the point now? Up to this, everyone is clear? Yes or no? Okay. Is everyone clear with these 2 points? No, it is not an equation of SVM. It is the hyperplane equation. See, the we are creating a hyperplane that is passing through the support vectors on the positive side. This is the positive side, okay? And we are creating an equation of a hyperplane which is passing through support vectors on negative side. So this is the hyperplane. This is another hyperplane that is parallel to this particular hyperplane that we have created. This is the hyperplane that is separating our data, and we are trying to maximize the margin. That is, we are trying to maximize the distance of these two support vectors on positive and negative side. So what we are doing is we are trying to pass a line hyperplane through both of the side. Okay, from the negative as well as the positive, on the positive as well as the negative, and we are defining the equation of both of this. So for example, we have already defined the equation of the hyperplane that we have, that is W x transpose X plus B equals to 0, and now W transpose X plus B equals to 1 is the equation of this hyperplane, and W transpose X plus B is equal to -1 is the equation of this hyperplane. Are you getting the point? Yes or no? Okay. So now what we'll be trying to do is maximize this margin distance. That is, we'll be trying to identify that what is this distance D, what is this distance value D, which we have to maximize, and ultimately we have to find the values of W and D such that this distance D is maximized. Okay, are you getting? So first, what we have defined a family of equations for both the sides, for hyperplane on both the side as well as the separating hyperplane. This is the family of equation that we have created, and we have utilized 1 and -1 for mathematical convenience. We can also use 25, 35 or any other values we can use, but for mathematical convenience, these are the lines that are parallel to this hyperplane. Okay, on both the side, these are the lines that are parallel to the hyperplane that we have created. That's why we are utilizing 1 and -1 for mathematical convenience at this point of time. Okay, I suppose up to this everyone is clear. Now we'll be proceeding to identifying the value of D at this now. Up to this, is everyone clear up to this? Okay. Anybody is having any doubt? I suppose nobody is having any doubt, so we'll proceed with the next part. Now, so before we proceed, we'll define a certain decision rules. Okay, decision rules. So if you recall, what was the decision rule in the case of logistic regression was W transpose X plus B. If suppose this value is greater than 0, then it was identifying in the 1 class, and W transpose X plus B is less than 0, then it was identifying in the -1. If you are right now, we are taking 1 and -1 as 2 classes in which we are trying to classify our data. 1 and -1, right? So the yi value. So all the data points that you have in the training set will be having xi as well as yi value, where xi is your features and yi is your target variable, right? So all the data set will be having, entire data set will be having in the pair of, it will be in the pair of xi and yi. So in this case, we are identifying that there are 2 classes, -1 and +1. These are the 2 classes. These are the 2 values that yi, that is the class label, will contain. Now, in this case, if you see where support vector equation is the line equation, the plane hyperplane equation is W transpose X plus B equals to 1 for the hyperplane on the positive side of the data, and W transpose X plus B is equals to -1 on the negative side of the data. Now if you see, if you try to multiply yi into W transpose X plus B, Suppose you are trying to find equation like this. Suppose you are trying to find an equation, a generalized equation like this. Then if you see for all the correct classification, this value will be always greater than equals to 1. Yes or no? This value will be always greater than equals to 1 for all the correct classification. Are you able to see why? See, for the case of, for example, let us consider for yi is the target variable. Yi is the target variable. Okay, let us go through in detail. Okay, see, now we are trying to create a decision rule. Okay, decision rule in this case. Decision rule means, for example, if the point W transpose X plus B is greater than 0, then it will be classified into C1 class, and W transpose X plus B value is less than 0, then it will be identified in the C2 class. For example, let us consider the hyperplane equation that we have is 2x plus 3y plus 3 is equals to 0. Something like this is our hyperplane. And we have a value, we have a point here that we are trying to classify. Suppose the point that we are trying to classify is 4, 4. This is the point that we are trying to identify, that whether this point will lie in the positive side of the hyperplane or in the negative side of the hyperplane. What we'll be doing? So we have this equation is similar to W1x1 plus W2x2 plus W0 is equals to 0. Yes or no? This equation is similar to that. Which is ultimately our hyperplane equation, where W transpose X plus B is equals to 0, where B is similar to W0 and W transpose is our parameter value, which is W1, W2, W3 and so on, right? Okay, so what we'll be doing? We'll be using this new value, that is X1, X2, 4 and 4 in this equation. So 2 into 4 plus 3 into 4 plus 3 is equals to greater than 0. So it will be lying in the positive side of the hyperplane. We can ultimately say this is a decision rule that we were utilizing in a normal linear classifier that we were using, right? Okay. Similarly, if we have a point, suppose our point is minus 3, 2, something like this is our point. Let us consider this is our point. Then this value will be 2 into minus 3 plus, let us say 3 into 1 plus 3, which is less than 0. This value will be less than 0. Then we can say that this point is lying on the negative side of the hyperplane. Okay. So this is the decision rule that we normally have in the case of in the case of linear classifier. This is the decision rule, normal decision rule. But in this case, we are trying to say is yi into W transpose X plus B is always greater than 1 for all the correctly classified points. Why it will be greater than equals to 1 for all the correctly classified points? If you see, yi can take two values, 1 and minus 1. Okay, these are the two values that yi can take. And now W transpose X plus B will be greater than 0. Will be greater than 0 for all the positive side of the hyperplane, and will be less than 0 for the negative side of the hyperplane. So if you see, for yi, suppose on the positive side of the hyperplane, yi value will be 1, and this value is also greater than 0. So it will be some positive value. So this value will be greater than equals to 1. But on the support vectors, what will be this value? But on the support vectors, this value will be equals to 1. Yes or no? Why? Are you getting this? Similarly, on the negative side, yi value will be minus 1. And yi value will be minus 1, and this value can be some positive value or can be some negative value. This is actually a distance value that we have. So it will be actually less than, positive or negative distance that we'll be having. So the total value will be greater than equals to 1, but ultimately on support vectors, this value will be equals to 1. Are you getting these 2 points? Yes or no? Yes. What about others? See, on support vectors, what is the equation? We are trying to find, we were passing in hyperplane through the support vectors. Okay, so this so the family of equation that we had created was a hyperplane equation which was W transpose X plus B equals to 0 and W transpose X plus B is equals to 1 for positive side of the hyperplane that we were passing through a support vector, and W transpose X plus B is equals to minus 1 was the equation of the hyperplane that we were passing through the negative side, on the negative side that we had created. So in short, we had created 3 hyperplanes in our data set. So this was the hyperplane. This is the actual hyperplane that is separating your data. And we have certain support vectors. We have certain support vectors that are closer to this hyperplane. So we are passing a hyperplane through these support vectors also, right? Is 0 on support vectors? No, it is equals to 1. Yes or no? See, if this is the equation of line, what is the equation of line on of positive side? W transpose X plus B equals to 1. Yes or no? So ultimately, the points that are on this for support vectors, this value will be equals to 1. W transpose X plus B will be equals to 1. Yes or no? And similarly, for this support vectors, this W transpose X plus B will be equals to minus 1. So ultimately, can you say that yi into W transpose X plus B for is equals to 1 for all the points which are support vectors? And for rest of the points, it will be greater than equals to 1. Yes or no? Are you getting this point or not? So for all the classification that is correct classification, for all the points that will be correctly classified, this value will be always greater than equals to 1. Because if you see, yi is the value, is the target attribute value, is the target value that your data set can take. It can take 2 values, plus 1 and minus 1. Suppose your data set is getting misclassified. Suppose your actual, suppose for an example, consider the x1 is an example that we are taking. And suppose the actual label of this class is plus 1. And suppose the value of W transpose X plus B that you are getting is less than 0. Okay, less than 0 that you are getting. So ultimately, the model is trying to say that the point is on the negative side of the hyperplane. So this value will be less than 0, less than 1. Yes or no? This value will be less than 1. So you can say that the point is misclassified. So for all the correctly classified point, this value yi into W transpose X plus B will be always greater than equals to 1. Are you getting this? Okay. Okay, I suppose everyone is clear with this point, right? So what we defined just now, we created a hyperplane. We defined an equation of hyperplane that we have. Equation of hyperplane is W transpose X plus B is equals to 0. This is the equation of the hyperplane that we have. Then we created 2 other hyperplanes on positive side as well as on the negative side of the actual hyperplane. Okay, passing through the support vectors, and we defined the equation of them also. This is the equation W transpose X plus B is equals to plus 1 for the equation for the hyperplane on the positive side, and W transpose X plus B is equals to minus 1 for the equation on the negative side. Okay, then we defined a decision rule where the class will be plus 1 if W transpose X plus B is greater than equals to 0, and will be C2, will be defining C2 is equal to minus 1 if this value is less than 0. Ultimately, for correct classification, our idea is if yi into W transpose X plus B is always greater than equals to 1 for all the points that are correctly classified. For all the points that will be correctly classified, this value will be always will be greater than equals to 1 and will be equals to 1 for all the points that are support vectors. Okay. Okay. So in this case, whatever such that, so we have to find the margin distance. We have to find the maximum margin distance such that all the points that we have, all the x1, x2 up to xn points that we have in our data set is correctly classified. And what is the correctly classified means? That yi into W transpose X plus B is always greater than equals to 1 for all the points. So we have to find a maximum margin distance such that this condition is satisfied. Are you getting the point now? Is everyone clear with this? Okay. So if you have any doubt, just you may unmute yourself or ask in the chat box also. Do not hesitate. Okay, so we have defined all of this. Now our next target is to find the value, find the equation of D. That is the margin distance. Okay, we have found the condition. First, we have to maximize the margin distance and we have to find a hyperplane equation such that this condition also needs to be satisfied, where yi is our target attribute value. yi is the target attribute value means it is present in your data set that is given to you. Okay, yi is the target attribute value that will be given in your data set, and w transpose x plus b we are calculating based on the equation of the hyperplane. We are trying to calculate this distance, and we are trying to will be considering the data set is correctly classified where if all the values is greater than equals to 1, and if this value is less than 1, then the point is misclassified. Okay, point is misclassified. And we have two cases in the case of margin that we have defined. We have hard margin and we have soft margin. Okay, what is hard margin, what is soft margin? Now, in this case, if you see the hyperplane that we have created, and these are the points. Consider these points on the positive side of the hyperplane and these points on the negative side of the hyperplane. So, in the case of hard margin, no point on the positive side will be allowed to be placed over here in between the after the on the negative side. Okay, in short, we are allowing no misclassification as well as no misclassification error. Whenever such a case is there, it is called hard margin. That is, no points on this side of the plane is allowed to be placed over here, or no points on this side. Just a minute. Suppose these are the points on the positive side. Then none of the points can be placed over here or over here. Okay. So this is hard margin where no misclassification error will be considered while calculating the margin. And if you see, if there is any case where a support vector or a point is being placed in the wrong side of the hyperplane, then this ultimately we won't be able to find this the margin equation, because we have to satisfy this condition in order to find the margin distance. Wherever condition is yi into w transpose x plus b must be greater than or equals to 1. This condition needs to be satisfied in order to find a margin, which is maximum margin distance and the hyperplane equation. So this is known as hard margin case, where we are allowing no misclassification error. Okay. But in the case of soft margin, we'll be allowing certain misclassification error. That is, we'll be calculating certain zeta value, which is the error value for this particular point. For example, there may be certain points which are placed on the wrong side of the hyperplane, and we are actually adding this error in the margin that we are calculating. So we are allowing certain misclassification error in the case of soft margin. Are you getting the difference between hard margin and soft margin? Okay. So now we'll proceed with defining the equation of margin. Okay, and we have a condition. We have already defined the condition that we need to satisfy in order to identify the maximum margin. That is, w transpose x plus b must be greater than or equals to 1. And we have our data set. We have a hyperplane equation. We have a set of hyperplane equation, that is w transpose x plus b is equals to 0 is the equation of the hyperplane that we have. And we have two other hyperplanes, one on the positive side and one on the negative side, where this equation is w transpose x plus b is equals to 1, and this equation is w transpose x plus b is equals to minus 1. Okay, and now we are trying to identify this distance d, right? for defining this, there may be multiple ways that you can solve this, but I'll be utilizing one of the methods to identify the distance value. One of the method, you may utilize vector form of data, vector in the using vector algebra. You may try to solve this, right? So let us consider there are 2 points. I'm considering one support vector over here, one support vector over here. Let us consider this support vector that we have is x1. I'm defining this support vector as x1 and defining this support vector as x2. And this is the distance between the support vectors. That is x2 minus x1 will be the distance of the will be the equation of the line. And do you know this theory? If you are trying to project one vector on another vector, what is the equation that we are creating? What is the idea? Do you know this or not? Yes, no. Suppose we have two vectors. Oh, just a minute. Okay. Ultimately, this value will be d. Okay, this value will be d. And I suppose that you know that also we need to define one more thing. We are trying. If you know this w is actually a vector which is orthogonal to the hyperplane. Orthogonal to the hyperplane. And it is also known as normal vector. Do you know about normal vector, which is we are trying to define w, which is orthogonal to the hyperplane, means the angle between both of them will be 90. And suppose we are trying to, if you know this particular theory that we'll be utilizing in the case of this is, suppose we are trying to project a particular hyperplane, particular vector on another vector, something like this will be there. Suppose there are two vectors A and B. This is a vector A and this is a vector B. And suppose we try to project the vector A on vector B. So it will, the result will be dot product between vector A and B. Do you know this? Yes or no? Okay. Yes. Please let me know in the chat section whether you know this or not. Okay. Okay. Yes, Priyank, I think this comes in vector algebra, but this is one concept that I'll be defining. For those of you who are not aware of this concept, this is one thing that you need to know is whenever you are trying to project a vector A on vector B, it will be resulting into the dot product of this vectors, that is vector dot product of this form. Okay, this is one thing. Just take it as it is. For those of you who are not understanding at this point of time, you may try to understand this. You may try to watch some videos regarding this vector algebra so that you will be able to understand what they are trying to do. But I suppose that others are clear with this. No need to uh, uh, go in depth of this, but this is an this mathematical point will be utilizing to solve this particular equation, that will be utilizing to solve this particular equation that we are trying to identify. We are trying to identify the value of the distance, but we'll be utilizing this particular mathematical concept to identify this distance. That is what we are trying to do. That's why I defined this. You may try to know further about this by studying certain online videos or something to understand better. But this is one concept that will be utilizing. But I think I suppose that is clear, right? So we'll be going in depth about the equation. We'll derive the equation in the next lecture. But I suppose the main theoretical point of today's lecture is clear about support vector machine. Right now we are don't have time, so I'll be just revising what we went through in today's lecture. So we started our discussion with support vector machine and why we are utilizing a support vector machine in the case of and what is the benefit, what is the idea, what idea does it So in the case of what the idea is that is we are trying to identify identify a hyperplane which maximizes the margin distance, and the margin distance is between the support vectors that we have on either side of the hyperplane, right? And we studied about 2 points, that is hard margin and soft margin. In the case of support vectors, hard margin does not allow any misclassification error, while soft margin will be allowed to go through some of the misclassification error, and we'll be considering that misclassification error whenever we are defining the distance d, that is the margin distance d, right? So in the next lecture, we'll be defining that we'll be trying to identify what is the margin distance in the case of support vector machine, and we'll be also going through the optimization of this support vector optimization algorithm that we'll be utilizing in order to maximize the distance. Okay, we'll be going in depth of that. I suppose this up to this everyone is clear in this particular lecture, right? So I'll end this meeting now, and if you are facing any difficulty, we'll go through that in the next lecture. Keep that in the next lecture. We'll discuss, right? Fine. I'll end the meeting now.